So, have you ever stopped to think about how your computer actually remembers anything, like your password or even just the last letter you typed? Well, it's not magic, it's all about memory. And today, we're going to pull back the curtain and look at the tiny, ingenious little switches that make our entire digital world possible. All right, here's our game plan. First, we're going to tackle why we even need memory in the first place. Then we'll meet the most basic building block, the latch. After that, we'll level up to its smarter cousin, the flip-flop, check out its whole family of different types, and finally, see how these two stack up against each other in the real world. Sound good? Let's get into it. Okay, so first things first. To really get why memory is so important, we have to understand the problem it was designed to solve. See, the earliest electronic circuits, they were kind of forgetful. They were purely reactive. They could process information, sure, but they couldn't hold on to it for even a second. So the big question for early engineers was, how do we make a circuit that can actually remember something? Yeah, seriously, think about it for a second. When you type a single letter on your keyboard, how does the computer remember that letter long enough to actually put it on the screen? It happens so fast we don't even notice. But, like I said, it's not magic. It's all thanks to circuits that are specifically designed to have a memory. So the secret really lies in two different kinds of circuits. You've got your combinational circuits. Think of these like a simple light switch. The light is only on when you're actively pressing the switch, right? It has absolutely no memory of what happened before. But then you have sequential circuits. Now these are different. Their output depends on the current input, sure, but also on past events. And it's all thanks to having memory built right in. So it's clear we need some kind of memory element, right? A building block that can hold on to information. Well, the simplest, most fundamental version of this is called a latch. And this right here is where our journey into digital memory really begins. Okay, so what is a latch? It's the most basic memory element you can make, and it's ingeniously built from just a couple of simple logic gates. The key idea is that it's bistable. That's just a fancy word that means it has two stable states. Think of it like a seesaw that's always tilted one way or the other. It never rests perfectly flat. One side is 0, the other side is 1. It literally latches onto one of those values and holds on tight. But how does it actually remember? Well, the magic is all in the feedback loop. Just look at this diagram. You can see how the output of one gate is fed right back into the input of the other one. This creates this awesome self-reinforcing loop. Once you tell it to be a 1, for example, the gates just keep telling each other, hey, stay a 1, stay a 1. And they'll keep doing that, effectively remembering that value, even after your original signal is long gone. Pretty clever, right? Now, latches are really clever, but they do have one big flaw. They're a little too responsive. This can cause all sorts of timing problems and weird, unpredictable behavior in bigger circuits. So to fix this, we need a smarter, more disciplined approach. And that brings us to the flip-flop. So here's the problem in a nutshell. Latches are what we call transparent. Basically, as long as the gate is open, any change on the input flows straight through to the output, instantly. It's like a clear window. But that constant sensitivity is a nightmare for complex systems, where you need everything to happen in perfect synchronized time. And the solution? The flip-flop. The name's kind of goofy, I know, but its job is serious business. The absolute genius of the flip-flop is that it's synchronous. It moves in perfect lockstep with a system clock. Think of it like a metronome for the circuit. It will only look at its inputs and decide whether to change at the exact instant the clock gives it the signal. It brings order to all that potential chaos. Okay, if you remember one thing, make it this. This is the absolute key difference. A latch is level triggered. That means it's paying attention for the entire time the clock signal is high. It's an open window. A flip-flop, on the other hand, is edge-triggered. It doesn't care about the level. It only acts in a single, instantaneous moment, the transition, the very edge of the clock pulse as it goes from low to high or from high to low. It's more like a camera shutter than a window. And this diagram just shows that perfectly. On the left, you've got a positive edge-triggered flip-flop. See how it only acts on that rising edge of the clock signal, that one tiny moment it goes from low to high? And then on the right, the negative edge-triggered one does the opposite. It only cares about the falling edge. This incredible razor-sharp timing is the real secret behind the stability and speed of pretty much every modern processor. So now that engineers had this amazing clock control, they didn't just stop with one kind of flip-flop. Of course not. They created a whole family of them, each one designed for a specific job. You can think of them as a toolkit for building digital circuits. All right, let's do a quick meet and greet with the family. First up, the SR flip-flop. It's the most basic one with simple set and reset inputs. Then you have the D flip-flop, which stands for data. This one is super useful. Its entire job is to just grab whatever data is at its input right at the clock edge and hold it. And then you've got the JK flip-flop. This is the powerhouse, the Swiss Army knife of the family. It can do everything the others can, plus it has this awesome toggle mode, which is absolutely essential for things like building counters. Okay, time for the main event. Let's put everything we've just learned together and have a final showdown. Latch versus flip-flop. Let's see how these two fundamental building blocks of memory really stack up. So, when it all comes down to it, what's the bottom line? Latch versus flip-flop. What are the key things you really need to know? This table really lays it all out. The number one difference, again, is the triggering. Latches are level sensitive, flip-flops are edge sensitive. Because of this, latches are faster and great for asynchronous systems, circuits that don't have a central clock and just react to things as they happen. The downside, they can be prone to weird glitches. Flip-flops, though, are built for synchronous systems. Think of your computer's CPU, where everything has to happen in perfect time with that master clock. They're a bit slower because they have to wait for the clock edge, but their immunity to glitches makes them the stable, reliable workhorses inside things like registers and counters. Okay, now for the really cool part. We've talked about the theory, but let's see how these simple little 1-bit memory cells come together to build the actual technology we use every single day. So where do you actually find these things? Honestly, everywhere. They are the absolute foundation for critical computer parts like registers, which are just temporary storage spots for data your computer is working on right now. They're used to build counters that track events. They're even used in circuits that divide frequencies. They are truly the workhorses of all digital logic. And this is how you go from small to huge. Remember, one flip-flop stores just 1 bit, a single 0 or 1. But line up 8 of them side by side, and now you have a register that can store a whole byte. That's enough for a single letter of text. Now imagine stacking thousands or millions of these registers together, and you've basically got the blueprint for your computer's RAM. So here's the really critical takeaway. Every single time your computer does anything, adds 2 numbers, renders a single frame of a video, or even just moves your mouse cursor across the screen, it is using registers made of these very flip-flops to temporarily hold and work with that data, millisecond by millisecond. It's kind of mind-blowing when you think about it. From these incredibly simple circuits, these tiny little switches that can only remember a single 1 or a 0, we have managed to build our entire digital universe. It is just incredible. And it really makes you wonder, right? What's next? What fundamental new discovery, what new building block is going to power the technology of tomorrow?
Thanks for watching, and please like, share, and subscribe for such more content and appreciation. Make sure to comment your questions and